Welcome to this explainer. Look, if you've ever been on call, you already know the pure, unadulterated adrenaline spike of a 3 a.m. system outage. Today, we're going to put on our senior architect hats and run a proper postmortem on one of these incidents. Our goal? To uncover the absolute critical difference between monitoring and observability. We're looking way past basic CPU metrics to see how hyperscale engineering teams actually survive the chaos of modern distributed systems. Here is our postmortem runbook for today. We'll start with a 3 a.m. page of reality, then break down monitoring versus observability. Next, tracing the microservice maze, stepping through a real debugging workflow, obsessing over P99 latency, and finally, engineering for true resilience.
All right, part 1, the 3 a.m. pager reality, or as I like to call it, when green dashboards lie. Imagine this scenario. It's 3 a.m. Your pager is screaming. You frantically open your dashboards, bracing for the worst, and everything is green. The CPU is totally fine, servers are up, memory looks great, but your users literally cannot check out. Your dashboards are lying to you by omission. Why? Because as Amazon's engineers perfectly point out, in modern distributed systems, we absolutely must accept the components are going to constantly fail. Networks partition, instances restart, disks stall out. The goal of engineering isn't preventing failure, it's building a system that functions despite those constant localized failures. Operating with broken parts is just a normal mode of operation.
Which leads us to the most frustrating question every engineer asks when a hidden latency spike or a massive retry storm brings down a core business function. Why on earth didn't our monitoring catch this? How did a tiny, localized failure in some non-critical background microservice cause an exponential growth in traffic that nuked the entire checkout flow? Well, to answer that, we have to admit a hard truth. What most teams call monitoring is fundamentally broken for modern architecture. Moving to part 2, monitoring versus observability. Let's actually define the difference. Because let's get one thing straight, these two terms are not interchangeable buzzwords. We need to draw a hard line here. Monitoring tells you that a symptom exists. It basically answers the question, is the system working? It's a binary state. It's up or it's down, it's fast or it's slow. Observability, on the other hand, is what actually lets you debug the root cause in a wildly complex microservices architecture. It answers the question, why isn't the system working? Think of it this way. Monitoring is checking the patient's thermometer, but observability is performing the MRI. To get that MRI-level detail, you need the 3 pillars of observability. First, metrics, to understand your steady state. Second, logs, to see isolated component states. And third, request tracing, for end-to-end flow. But here is the massive catch that trips up so many teams. Having these 3 pillars means absolutely nothing without correlation. If your tools are siloed, you are flying blind during a major incident, desperately copying and pasting trace IDs between browser tabs while your mean time to recovery completely skyrockets.
So let's talk about tracing. Part 3, tracing the microservice maze, finding the needle in the haystack.
30,000. I want you to let that number sink in for a second. In modern, highly distributed environments, like Uber's architecture, for example, a single user request, like simply booking a ride, can easily traverse 500 discrete microservices and trigger over 30,000 remote procedure calls. 30,000 potential failure points for one single action. If a request slows down, just guessing where the bottleneck is simply isn't an option anymore. Take a typical request path. A user clicks a button, which hits the API gateway, which calls the auth service, which drops an event in a message queue, which finally triggers a database query. In a legacy monolith, you just tail the database logs. But in microservices, you absolutely need a distributed trace to attach a single unique ID across this entire transaction boundary. Otherwise, you might see that the database is running slow, but you'll have absolutely zero context on which upstream service actually sent the toxic query that choked it in the first place. And this is exactly why checking infrastructure saturation just doesn't cut it anymore. Look at where the focus lies. Infrastructure metrics tell you if the machine is healthy, but business metrics tell you if the user is happy. If your CPU is sitting at a comfortable 40%, but your checkout success rate drops to 50%, you are in the middle of a massive outage, no matter how green your infrastructure dashboard looks. You absolutely must monitor the actual business steady state. Which brings us to part 4. A real debugging workflow. Let's get pragmatic about how we handle these pages. When the pager actually fires, the very first thing you do is look at the 4 golden signals. Pioneered by the SREs over at Google, these are traffic, errors, latency, and saturation. You can instantly gauge the health of your user-facing systems by checking these 4 key metrics. How much demand is hitting the system right now?
What's the rate of failing requests? How long are those requests taking? And how full are your constrained resources, like connection pools or CPU threads? Seriously, if you only have time to look at one dashboard during a fire, make sure it has these 4 signals. So you identified the anomaly. Now follow the golden rule of incident response. Mitigate first. When the adrenaline is pumping, it is incredibly tempting to investigate the deep root cause. Or worse, deploy a quick hotfix to solve the bug live. Do not do it. Trying to forward fix in production during an active outage almost always triggers a secondary outage. Roll back the recent code deployment. Shed the incoming load. Flip a feature flag off. Get the system back to its steady state first. You can investigate the root cause the next day when you're actually awake, and then follow it up with a deep, blameless postmortem.
All right, part 5, obsessing over P99 latency. Because honestly, average is a lie.
When you finally sit down to write that postmortem, your observability data is probably going to reveal a really harsh truth. Average latency is a complete lie. Why? Because the mathematical average smoothly hides the 1% of requests taking 2, 3, or maybe 5 seconds to complete. You have to look at P99 latency, the 99th percentile. As senior Google engineers have pointed out, composing many sub-requests makes high percentile latency absolutely explode. Think about it. If one user request hits 50 different microservices, and each of those services has just a 1% chance of being slow, almost every single user request is going to hit that tail latency somewhere along the chain. In distributed systems, rare slow events are no longer rare. They literally become the defining characteristic of your user experience. To really conquer that tail at scale problem, AWS architecture guidance provides a brilliant hierarchy. You have to break your telemetry down into business metrics for your steady state, server-side metrics for saturation, and client-side metrics for the true user experience. If you only profile the server CPU, you completely miss all the hidden wait time, like threads locked waiting on a flaky downstream network call or weird database locks, and that hidden wait time is exactly where the real user-killing latency hides. Finally, part 6, engineering for true resilience. Let's actually architect the fix.
Identifying the bottleneck is great, but it's only half the battle. Now we have to fix the architecture so it doesn't happen again. We apply senior design patterns to prevent cascading failures like retry storms. First step, aggressive caching with something like Redis for those expensive, heavy queries. Second, idempotency keys. Giants like Stripe and Uber use these constantly. A unique ID guarantees that if a network drops during a payment flow, an automatic retry won't double charge the poor user. Third, strict latency budgets and aggressive timeouts per network hop. And finally, circuit breakers, so you can shed bad load before the entire system goes down in flames.
At the end of the day, performance is a property of your entire distributed architecture, not just a single server sitting in a rack. You absolutely need those correlated metrics, traces, and logs to map out the butterfly effects in your system. So, when you log into your telemetry tools tomorrow morning, I want you to ask yourself a serious question. Are you just staring at your system's symptoms, or are you actually equipped to observe its true behavior? Keep digging into those traces, build resilient systems, and I'll catch you in the next explainer.